That's your plan for Friday? Oh, that's awesome. All of it.
Okay. So actually, before we do this, just a heads up. I know you guys want your midterms back. Sorry, we've had some trouble getting those to you. We thought that there was a locked cabinet to store those in G130. Turns out the cabinet doesn't actually have a lock. So FERPA says that we can't put your exams there. So I have all of your exams. Those of you that want them, I have them with me during office hours, and I'll be storing them in the ME office where our TAs will check them out every time they do TA office hours. In the meantime, I've also gone ahead and uploaded the solutions key to the first midterm to Icon, so that's under the Exam 1 prep materials. And that includes detailed solutions and rough grading breakdowns for the exam. So you can pick up your exams, compare against the key, and certainly if you have questions, you're welcome to come and talk to me. So today we're going to be talking about the beginning of Chapter 6, right? Fluid element kinematics. So we've talked about kinematics so far, right? We introduced the idea of kinematics in Chapter 5, kinematics being the way that different components of motion are interrelated. We're going to take that down now. Instead of working with finite control volumes, we're going to work with very small differential or infinitesimally small control volumes, or what we call differential fluid elements. So today is going to be about defining and understanding how the different components of motion, namely translation, dilatation, rotation, and rate of shear, are related to general fluid motion. Okay, and with those tools, we should then be able to say, given a velocity field, can we determine A, whether it satisfies continuity, the continuity equation, and B, can we say whether a velocity field is rotational versus irrotational? And this will take us into topics such as vorticity and some personal favorites of mine. So I've got some, hopefully we'll have time to show some interesting videos of different types of fluid motion. So the first step when going from big control volumes, right, to very tiny little control volumes is understanding exactly how the fluid moves. Oops. So we're going to start out by assuming we're going to zoom in on a flow, right? So if we have a little square or a cube of fluid, okay, and we assume that this thing is vanishingly small. And by vanishingly small, I mean it's delta x tall, delta y, or delta x wide, delta y tall, delta z into the page, okay, and that these delta x, delta y, delta z are all approaching 0. Okay, so this is effectively a point in space, but it's a square-shaped point in space. We're going to zoom in on this. We can describe the motion of that little square using 4 kind of building blocks. And rather than drawing them, I'm going to go ahead and just rely on PowerPoint to do the art for me. Okay, so if we start out with that cubic shaped fluid element, then if we fast forward some amount of time, we can understand that it's probably going to move. If there's a fluid velocity, it'll move. Additionally, we could count on it probably to change its shape. And so general motion involves this motion and this shape change. So what we're doing now is we're saying we can decompose that motion into linear motion and angular motion. Okay, so moving, rotating. But under each of those, right, for linear and angular, there is both the actual motion and then there's deformation. So the first of these would be, right, translation, which is pure linear motion. Then we have what's called dilatation or linear deformation. Okay, so there are linear components. Then this is sort of rigid body rotation, simply spinning. We call this angular motion. And then there is angular deformation. Okay, so we have these 2 species of motion, and each one has a motion and deformation associated with it. So we're going to briefly step through each of these and relate it back to a velocity field and see how we would calculate each one of these components. Oh, come on, I want to leave. Go. Okay. So, a little recap here, right? We've established that a velocity field is a velocity given as a function of x, y, z, and t, right? Function of space and time. Should be u, x, y, z, t in the I direction plus v of the same quantities in the j direction plus w as a function of the same quantities in the k direction. So the first type of motion, linear motion, also known as translation. If we start out with our square and we label the corners A, B, C, and D, if we have a velocity field v of x, y, z, and t is simply equal to v naught for all space and time. Then, in other words, we have a completely constant velocity in the background. It doesn't change from point to point, and it doesn't change as a function of time. Then, if we start at this point and we fast forward some short time later, right? If we allow a time of delta t to elapse. Let me draw it down here. Come on, make me a square. I don't know why we're not getting square, but our points, right? Our A, B, C, and D points are going to translate to A, C prime, D prime, right? They're all going to translate by the same distance. And so all that's really been accomplished here is that every point has moved. Now it changes my. Is that every point has moved v naught times delta t. So we have this simple, pure translation of our box from one place to another. So we can say that translation involves pure, rigid body motion, and it can only occur when v is constant. In other words, there are no velocity gradients. Okay, the second type, linear deformation, also called dilatation or dilatation. It's a pronunciation that is not fairly clear. So if a constant velocity causes our box, our square, a fluid simply translate in space. What happens if the velocity is not uniform? Specifically, what occurs if the velocity varies in the direction of motion? For example, let's say that v of x, y, z, and t is equal to, right, u of x only plus 0j plus 0k. This would suggest that the horizontal component of the velocity is a function of the horizontal position in space. So if we start out, let me just, there we go, A, B, C, and D. This is at time equals 0. If we wanted to write the velocity at each corner here, we could say maybe the velocity at A is u, okay? Velocity at D is u because they have the same x coordinate. The velocity at C we might say is u plus du dx times delta x, right? So this is an application of the first order Taylor series that we've been using in the past, right? Where we say we know that u changes with x, but we don't have a functional description of it necessarily. We can simply approximate a change over a short distance by multiplying that short distance by the gradient. U plus u dx times delta x. So the idea here is that the left side is moving, but the right side is moving faster. So at some instant in time, at t equals delta t, a little later, our initial square should have deformed. It will have elongated. Because that right side and its faster motion has outstripped the left side and caused it to stretch. So if we have a case like this, what we'd be interested in characterizing when we write this concept of linear deformation or dilatation is the rate of the change of the volume of this fluid element. So skipping over the derivation here, if we wanted to write the time rate of change of volume of this element A, B, C, D, we would end up with dV dt is equal to u dx times delta x, delta y, delta z. Or du dx times the little volume of that cube. More generally, so this is a case where the velocity is only changing in the x direction. If it's also changing in the y direction and in the z direction, okay, if we allow that three-dimensional velocity function to come in, then for u, v, w, all varying on x, y, z, we would write dv dt is equal to du dx plus dv dy plus dw dz dx dy dz. And the last thing we would do here is we would say, well, let me replace this with that delta v. And so the last thing we would do is we would write the rate of change of volume per unit volume. And that's simply going to involve dividing through by that delta v, the volume of the cube itself. So if you think of this, think of like courses like def bods and such, where you have, or any solid mechanics, the idea of like a strain, right, is the amount of elongation per unit length. It's a non-dimensional quantity. Okay, this is a similar idea. This is the rate at which the volume is growing per unit volume. So, oops. 1 over v times v dt is equal to du dx plus dv dy plus dw dz. And this can be thought of as the rate of change of volume per unit volume. If we recall back into our vector calc and vector identities, we could write this as quantity that we call the divergence of our velocity field. Okay. And so the physical meaning here, right, is that at a point in space, if we figure out the divergence, this is telling us how quickly the velocities are all moving away from each other. In other words, at a point in space, how quickly is that point trying to stretch out? So this at this point, it's helpful if we take a little aside, and we say, what can we say about this quantity? You know, what is this? I should probably tell you that this is actually, right? This is the definition of the volume dilatation. This is that quantity we've been looking for. So what can we say about the volume dilatation for a fluid that is incompressible? Any ideas? I heard a 0. Okay, that's simply because incompressible fluid, the idea there is it can't change its volume. Right, a given set of unit of mass cannot change its volume. It can't be stretched. It can't be compressed, as the name implies, and so this quantity has to, by definition, be equal to 0. So for an incompressible fluid, the divergence of the velocity field is equal to 0. And this is a very, very important identity. This is something that, this is the mathematical statement of what it means to have an incompressible flow. All right? Or rather, this is the mathematical statement of a velocity field for an incompressible flow. So we're going to talk about this. We're going to use this definition here next week when we talk about the actual definition of the continuity equation and momentum equations for one of these tiny little cubic control volumes. But for now, we're going to leave it at that and say that this is the form of the continuity equation for an incompressible flow. Okay, so quick example usage. If we're given a velocity field, it is 4xy I plus 2x squared minus y squared j. Does this velocity field satisfy continuity if we assume that the flow is incompressible? Okay, so take about 2 minutes and work out what you get for this quantity. All right, so show of hands, we'll do, if you got a yes, put up an open hand. If you got a no, closed fist. Does this flow satisfy continuity? We assume it's incompressible. All right, we're missing some hands. So, but the ones I do see are right. So this will satisfy the continuity equation. How do we get there? Start working out values. We know u and we know v, right? U is 4xy. V is 2x squared minus y squared, right? So we've got the I component and the j component. We have a 2D velocity field. Right? There's no z velocity, so we could go ahead and just say that w is equal to 0. Okay? So du dx equal to 4y. All right? dv dy be equal to what? Negative 4y. dw dz 0. So this divergence, right, is du dx plus dv dy plus dw dz. So if we calculate each of those quantities, add them up. In this case, we get 4y minus 4y equals 0. Which is telling us that the flow is not trying to expand or contract at any point. Okay? So it satisfies this idea that the mass of a fluid particle must remain constant if it's incompressible. Okay, so we've talked about the linear components of motion, right? Translation and dilatation. The other part of it is rotational. Okay, rotational motion is this sort of rigid body spinning, and then this rate of shear strain or this deformation that occurs. I'm going to be a little bit quicker and more informal with the derivations here. I know that the derivations of this stuff is no one's idea of fun, but we need to get to we need to at least gloss over them so that we understand kind of what does rotation actually represent. So rotational components. So what if we have these cross derivatives such as du, dy, dv, dx. We're going to quickly draw our little box again, say A, B, C, and D. And in this case, right, down here at A, we might say that we've got velocity u and v. Okay. Now let's assume that we've got, let's assume that du dx is equal to 0, dv dy is equal to 0. Then the resulting velocities over here are going to be, right, u v plus dv dx times delta x. Over here it'll be v and u plus du dx, dy times delta y. Once again, first order Taylor series. If the horizontal component of the flow is only changing in the y direction, then it's going to increase from u to this u plus the slope times the distance. Same thing with the velocity or the vertical velocity. And so as time elapses, what's going to happen to our nice square box is that these two legs, there we go, is that A, B, C, D. The two legs of this box, A and B, AB and AD, okay, are going to start to rotate. So we're kind of ignoring point C for right now, but if we just look at these two sides, what's going to happen is that, right, this side's moving up faster than this side's moving to the right faster than this side, and so they're going to start to rotate inward or maybe outward if it happens to be that the velocity at the top is slower than at the bottom. So we'll give the two rates of rotation here. We'll call this one omega AB, rotation rate of line segment AB, and we can write this as dV dx. Okay. If dV dx is positive, what direction is this going to be rotating? Clockwise or counterclockwise? Counterclockwise. Okay, so we'll go ahead and call this positive counterclockwise. Okay. This one up here, let's go ahead and change up the color scheme a little bit. We'll call omega AD. Right, similar idea is the rotation rate of line segment AD, which is equal to du dy. And is this one going to be, if du dy is positive, is it going to rotate clockwise or counterclockwise? If the top of the box is moving faster than the bottom of the box horizontally, it's going to be clockwise in this case. So we've got a little bit of a, this is an important thing that's going to come in just a second. So this is, right now, we're talking about general rotational motion. So what's going on right now, we're going to split into two parts. This here is the combination of rotation and deformation. If we were to, number 3, if we were to draw a line, let's say we draw the rest of our box here. Okay. If we were to draw a line between point A and C, okay, omega AC would be defined as the rotational rate of sort of the entire element. What component of this motion is causing it to actually spin? And we're going to go ahead, because we get to pick this one, we're going to go ahead and define this as being positive counterclockwise. In other words, following the right-hand rule convention. We can also say that, right, WAC is equal to the average of WAB and WAD. This is going to be 1/2 WAB minus WAD. Now the reason we've got that minus there is that we've gone ahead and decided that this is going to be positive counterclockwise, but WAD, right, is defined positive clockwise. And so we have to flip the sign on that so that we have the same convention on both of them. So this turns into 1/2 dV dx minus du dy. So that's the rotation of our fluid element. What direction, like what axis is this rotation occurring about? Z. Okay, so we would also call this the Z component of the fluid element's rotation. If we have other cross terms, for example, if there's a gradient in the Z component of the velocity or if the u and v components vary in z as well. We're going to have rotation elements about the x component, the y component, and the z component. But in all cases, they're going to be written this way. So we would define this vector, omega, as being wx, okay, in the I direction, plus wy in the j direction, plus wz, that's the one we just derived, in the k direction, which is going to be 1/2 dv, oops, sorry, that should be a dw, dy minus dv dz plus 1/2 du dz minus dw dx in the j direction plus 1/2, and here's the one we just did, dv dx minus du dy in the k direction. Okay, so the takeaway here is that fluid rotation is a three-dimensional vector. Similar to dynamics, right? This is telling us essentially what is the axis of rotation of our fluid element based on the velocity distribution near that fluid element. If we're not going to prove it to ourselves right now, but we can also write this as 1/2 the cross product of the gradient operator with the velocity. From vector, it's math 5, right? I think vector calc. Does anyone know what this quantity here is called? Curl. Right. So rotation is W is equal to 1/2 curl of the velocity vector. Okay, this is another major, very important definition. Here's the fun part. Fluid mechanicians have also added in a second quantity that they call vorticity, which they've given a way harder symbol to. Oops. This chi, all right? And this is simply equal to 2 times omega. That makes it equal to curl of V. I don't know why they gave it an entirely new name. Clearly, fluid mechanicians aren't scared of math, so multiplying it by 2 to avoid that 1/2 seems a bit superfluous. But we've got these two definitions of what amount to the same thing. Okay, rotation and vorticity. Vorticity is a really rich topic, okay? And it's probably a term you've heard before, but it's one of the most fascinating things in fluid dynamics, because the idea that when you have fluid elements that begin rotating, okay, similar to the way in our control volume analysis of the previous chapter, fluid velocity gets transported, right, as momentum. Fluid vorticity also gets transported, and it leads to a lot of really interesting physical phenomena. So things like, if I can make this play. Oh, come on. Is my YouTube embedding not going to work here? Let me try something here. Okay, well, things like the flow around airplane wings, okay, shown over here on the right is a simulation of flow past an airplane, where what they've done is they have created isosurfaces, right? This idea that they're gonna make a solid surface out of everything that some variable equals a certain quantity. And what they've done here is they've said we're gonna set isosurfaces of vorticity. Okay. So what that does is allows you to see these sort of tubes of fluid that are spinning. I've done a lot of work with viewing and measuring vorticity in my own research. So this is, let me move that out from behind the picture here real quick. Discard. I don't know why PowerPoint's just being a huge pain right now. Okay. So similar to the way you get vorticity on wings, this is research I did back in Michigan on a wing that's sort of underwater, where you end up with this huge vortex that comes off the tip of the wing, right? This spinning sort of filament of fluid, and in this case, that vortex is actually sucking up air from the free surface, sort of like a straw, and it creates this about 100-foot long air-filled rope underwater. And we actually can already explain why it is that occurs, right? When we talked about the Bernoulli equation applied across streamlines, one of the things we said is, right, if you have a streamline that's doing this, on which side is the pressure lower? Here, right? Streamlines curve towards regions of low pressure. So it makes sense that in a vortex where the streamlines are circular, that the pressure has to decrease as you move towards the center of that circle. And this is the reason that barometric pressure at the center of hurricanes and tornadoes is lowest. It also is the reason why things like that happen. You create a spinning rope of fluid at the center of that rope. The pressure has to get really small. If you put like air there, it sucks it up like a straw into that region of low pressure. Okay. I really hope that these ones work, because these are some really cool videos. No. Oh, maybe. Yes. All right. That's not going to fly. Let me find this one for you. Speaking of vorticity and tracking Hurricane Michael, it's there we go. So an example of kind of vorticity in nature, dolphins have, and other marine animals actually have, this incredible ability to sort of manipulate vorticity underwater. So what these dolphins are doing is, some of that video I just showed you, they're creating these spinning rings, okay, these vortex filaments. They're blowing air into them and they're playing with them like loops. This is something that that scientists couldn't do if we tried, right? It's the most complicated of robots. We just don't have this sense of the way fluid mechanics works. And so this is one of the, it's a little bit humbling, right? I have a PhD in fluid mechanics, and these dolphins are clearly way smarter than I am. There are some cool visualizations of the way that vorticity works. There's a friend of a friend that runs these, puts these videos online, goes by Physics Girl. She's got these really interesting, is it going to let me go full screen? Nope. Got these really interesting visualizations she did in a friend's pool of injecting dye into vortices. Is an experiment you can do in a bathtub or a kitchen sink where you drag a plate through the water and it creates half of the kind of ring vortex we were just looking at. And if you drop food coloring into it, you sort of begin to see the way that these vortex filaments behave. All right, we are just about, I need to we'll come back and look at another video here in a second, but I have to introduce the fourth component of fluid motion. All right. So at this point, we've tackled linear translation, linear deformation. This vorticity or rotation, right? It's a sort of rigid body spinning fluid. But the last component is number 4, shear or angular deformation. Okay. So if I scroll back up to sort of example here, right? We've said that the rotation tells us how quickly this line AC is rotating. Okay, the bisector of this fluid element. But what about the rate at which it's actually changing its shape? Okay, if A and B and A and D are rotating at the same speeds, okay, this thing is simply going to remain square and it's going to spin around like a block, pure rotation. But if the magnitudes of those rotational speeds don't equal one another, then we end up with shear deformation. So the way we write that is if rotation is the average of the two rotational velocities in a right-hand positive sense, angular deformation is the difference between them. So we're going to go ahead and write gamma dot or d gamma dt, where gamma is defined as, I'm going to keep scrolling up here. Gamma is defined as the angle between these two lines, right? So gamma is equal to the angle of line DAB. So gamma, d gamma dt can be written as omega AB plus omega AD, right? The plus sign here, right, is due to the fact that, once again, we're defining this as that omega AB and omega A naught, or A0, AD, I can't read my own handwriting. Omega AD are defined with different positive senses. So we have to flip the sign on one of them. We pick to flip the sign on omega AD so that it's right-hand positive, which means it takes on a negative sign. So taking the difference ends up being adding them together. And so this ends up being, right, dv dx plus du dy. And we would call this gamma dot, which is known as the rate of strain. All right, this is going to be, this quantity right here is not a scalar, or rather gamma dot is not a scalar, and it's not a vector. It's actually what we call a second order tensor. It's made up of a matrix. So in the very first beginning of this class, we defined the idea of what's a Newtonian fluid. Right? And the way we said that was that a Newtonian fluid is one where, right, shear stress is equal to viscosity times rate of strain. So this rate of strain here results from velocities that vary, in the u and v velocities vary with x and y. But again, what if we allow other variations in there? What if we allow our w in there? So the way we would write this is, in general, gamma dot, we'll call gamma dot ij is equal to the I component So I and j here indicate the components of the respective vectors. So, for example, v1 is equal to u, v2 is equal to v, right? v3 is equal to w. x1 would be equal to x, x2 is equal to y, x3 is equal to z, right? This indicial notation here. So looking at this, basically we're going to end up with this being a 3x3 matrix that tells us how quickly shear deformations are occurring as a result of variations of u, v, and w in the x, y, z directions. Okay. And we're not going to use this quantity very much explicitly, but this is going to be really, really important when we get into the general equations of motion for a fluid, the Navier-Stokes equations, because this allows us to relate the forces on a fluid, right, or a fluid element, the shear stresses, to the velocities in the fluid, okay, which is one of the important ways that we figure out how flows move. So a little bit of, I probably should have done this at the very beginning, right, but the reason we're actually going through this process, right, is that, so we spent the last week talking about control volumes, which are really useful because they allow us to kind of take a black box approach to engineering. We can literally draw a box around some engineering system. We can look at the flow going into it and coming out of it and come up with some engineering level result of interest. What's the lift on this wing? What's the force on this, this dredger? But it doesn't give us details of what's going on inside of the box. So the idea here is that we're taking those control volumes that were big and encompassed our entire system, and we're making them so vanishingly small that we'll be able to apply the same kind of approach, right? Conservation of mass, conservation of momentum, conservation of energy, and we'll be able to apply those to a bunch of little tiny control volumes that are adjacent to one another to resolve details of the flow. Things like, okay, what happens to the flow inside of a pipe? Okay, we'll see in the next lab that the flow through a pipe adopts a sort of parabolic velocity distribution. Why does that occur? Right? Shear stresses and pressures and flow past wings, and things that occur like flow past cylinders, right, which end up giving us this interesting kind of unsteady flow behavior called a von Karman vortex street. Again, more examples of vorticity. And so this lesson right here was meant to set up the way the fluids move, and we'll start building on that by saying, how can we relate that fluid motion to the forces that drive them and allow us to get here? So that's what I've got for you. I'll go ahead and post these slides online so you can look at the videos and browse through them.